Hey everyone, welcome back to the channel where we dive into the world of data science and machine learning. Today we are going to explore one of the most fundamental concepts you will ever encounter, that is linear regression. Sounds complicated? Don't worry, we'll break it down step by step, and by the end of this video you will understand it like a pro. Let's start with a quick roadmap of what we are going to cover today. First, we'll talk about what regression is and then zoom in on linear regression. Next, we will explore some real-life use cases where it shines. After that, I will break down the algorithm from scratch and will touch on how to measure the performance of our model using goodness of fit. Finally, we will implement everything in Python. Sounds exciting? Let's get started. First things first, what is regression? In simple terms, regression helps us understand relationships between two variables and make predictions. For instance, imagine you have data on the number of hours you study and the scores you get on a test. Linear regression helps us find a line that best fits these data so we can predict what your score might be based on how long you study. So, what is linear regression? It's a specific type of regression where we assume the relationship between the variables is linear. That means a straight line. It's one of the simplest yet most powerful techniques in machine learning. With linear regression, we are specifically trying to find the straight line that best describes the relationship between the input and output. This line helps us predict values for new data. The goal is to model the relationship between the independent variable, let's say study hours in our example, and the dependent variable, that is test scores, using the equation of a line which is y is equals to mx plus c, where y is the test scores, x is the number of study hours, m is the slope, how much y changes for every change in x, and c is the intercept where the line crosses the y-axis. But where is linear regression used in the real world? Almost everywhere. Predicting housing prices, forecasting sales, determining stock prices, and even in healthcare for predicting patient outcomes. In all these cases, there is a linear relationship between the input and output, which makes linear regression a perfect fit. Now comes the fun part. How do we find the best fit line? The first step is plotting your data points. Here, we have some data points for x, study hours, and y, test scores. Next, we calculate the mean of x and y. The mean gives us the average value and helps us to find the center point of the data. Now that we have the average, we need to calculate the slope m of the line. This gives us the angle or tilt of the line. It tells us how much y changes for each unit increase in x. The formula for the slope is summation of x minus x bar multiplied by y minus y bar divided by x minus x bar whole square, where x bar and y bar are mean of x and y value. So first we calculate individual components, that is x minus x bar, y minus y bar, multiplication of these two, and x minus x bar whole square. Then sum these value and put these value in the formula to get the value of slope as 10. Once we have the slope, we can calculate the intercept c. Intercept is the value where the line crosses the y-axis. We are using the formula c is equals to y bar minus mx bar, which is nothing but equation of line, and x bar and y bar are mean of x and y respectively. Great. Now we have our line equation y is equals to tan x plus 40. We can start predicting values for y based on new x values. From these graphs, we can easily predict test scores based on study hours. All the points completely lie in the regression line. But here's the catch. Our predictions aren't always perfect. There will always be some error between the actual value and the predicted value. So let's modify the values and then see. All the calculation remains same till the equation of a line. First, we calculate mean. Then we calculate slope using the same formula. We got slope is equals to 9.7. And similarly, we calculate intercept, which is equal to 40.1. And now the equation of line is y is equals to 9.7x plus 40.1. Our actual value doesn't match with predicted value. You can see in this table. The error is the distance between the actual data points and the predicted points on our line. Our goal is to minimize this error. To do that, we need a method called gradient descent. Gradient descent is an algorithm that helps us minimize the error by adjusting the values of m and c over time. Here's how it works. After each iteration, we calculate the error and tweak the values of m and c to bring the line closer to the data points. With every iteration, the line gets better at predicting values. We are minimizing something called mean squared error, which is the average of all squared error. We continue this process for multiple iterations until the error is minimized. Here we use formula of mean squared error as 1 by n summation of actual y value minus predicted y value whole square. We get mean squared error as 3.58. So now that we have our best fit line, we need to check how well it actually fits our data. To do that, we use something called R square. R square is equals to 1 minus sum of square differences between actual and predicted value divided by sum of square differences from the mean. Think of R square as a measure of how much of the variation in our data is explained by the model. In simple terms, it tells us how well the line fits. If the R square is 1, our model fits the data perfectly. If it's closer to 0, it means our model doesn't explain the data well. The R square value in our example is 0.9813, indicates that the model explained 98.13% of the variance in the test scores, which shows a very good fit. Now you can see the graph between study hours and test scores. Here you can see that points are not completely lies on the best fit line. They are slightly deviated. Let's put everything into practice. We will use Python and scikit-learn to create a linear regression model. Predict some values and then calculate the R square to see how well our model fits. And now we are going to run the code in Colab. Let's do it together. Open Colab. First, we are going to import all the libraries that we will require. First, I'm importing NumPy. Then I'm importing PyPlot from Matplotlib. Then I'm using linear regression model from sklearn. Next, I'm importing R2 score from sklearn.matrix. Run this. Okay, since it's done, first we are importing dummy dataset. X is equals to np.array. Here I am creating the dummy dataset. Since it's a dependent variable, we need to convert this in 2D from dot reshape. It will be our number of hours studied. Next, y. Y will be our test score. Since it's a dependent variable, we do not need to convert in 2D. We can directly write it. Okay, then run this. Okay, since done, now we are importing our linear regression model. Model is equals to run this. We are using this to train the model. Okay, since it's done, now we will fit the values into the model using model.fit. Run this. Okay, it's done. Now we use y pred to predict the data. Model.predict. Run this. It will predict test scores based on the input variable, that is our R studied. Okay, it's done. Now we'll calculate R2 score. Run this. It's done. Now print the R2 score. Run this. R2 score is used to measure how well our model predicts. It's showing 0.99. It's a very good. Next, we are going to plot our graph. We are using scatter plot to plot the actual points. Next, we are using plt dot plot to plot our linear regression line. Next, we will add X label and Y label. X label will be R studied and Y label will be our test scores. Next, add title. adding box and then show. Run this. Here you can see that the linear regression line is drawn between our studied and test scores. To wrap things up, we started with understanding regression, moved to linear regression and its use cases, broke down the algorithm, checked how well our model performs with goodness of fit, and then implemented it in Python. Linear regression is a foundational tool, and now that you understand it, you have unlocked a big piece of the data science puzzle. If you enjoyed this video and learned something new, don't forget to like, share, and subscribe for more such data science and machine learning related content. Thanks for watching, and I will see you in the next video.